Welcome to this session on classification as part of SAP BTP AI best practices. We'll explore how to efficiently identify patterns and data using SAP HANA machine learning tools. By the end of this session, you'll have a clear understanding of key principles, best practices, and implementation approaches to automate categorization of data into predefined classes. Our discussion will follow these 4 key steps. First, we'll provide an overview of classification and its benefits in the SAP ecosystem. Second, we'll cover the essential prerequisites you need to have in place, including supported environments and required components. Third, we'll explore key choices and guidelines that impact your implementation, including modeling valuation to understand how well a model is performing. Therefore, helping to identify areas for improvement and guide model selection. Finally, we'll dive into implementation approaches across programming models, providing concrete examples for Python. Classification is a fundamental machine learning technique aimed at organizing input data into distinct classes. In the SAP ecosystem, this involves leveraging SAP HANA machine learning tools, specifically Predictive Analysis Library, and HANA ML. The expected outcomes include recognizing patterns in the training data and using these patterns to classify new data into one of the predefined classes. Optimizing business processes by helping to group similar items together while distinguishing them from different ones, leading to improved understanding, prediction, and decision-making. Why use SAP HANA machine learning for classification? There are 3 main benefits. First, algorithm interchangeability. You can easily switch between different algorithms like logistic regression, random decision trees, hybrid gradient, boosting tree for classification, support vector machine to best suit your specific classification needs. Second, out-of-the-box features that supercharge your development with built-in capabilities for characteristic neighbor models, decision tree-based modeling, among many others. Third, security and SAP ecosystem integration. It's fully integrated with SAP technologies, leveraging enterprise-grade security and native in-database processing. These advantages make classification more efficient and accessible for SAP users. Before implementing classification solutions, let's cover the necessary prerequisites. You'll need SAP HANA Platform 2.0 SPS 04 or higher, or preferably SAP HANA Cloud for easier management. SAP's Data, Figures, or Express edition can also be used for specific scenarios. Application Function Library containing Predictive Analysis Library and Automated Predictive Library components. Script server enabled for executing machine learning algorithms provide more context. SAP HANA is an in-memory database enabling real-time analytics and applications. The HANA ML libraries, Predictive Analysis Library, and Automated Predictive Library provide native in-database functions for predictive analysis and machine learning. Script server is an auxiliary HANA process, essential for executing these machine learning functions. Setting up these prerequisites establishes a strong foundation for implementing effective classification solutions at scale. Let's examine the high-level reference architecture for classification using SAP HANA machine learning. The diagram shows the complete machine learning execution environment within the SAP HANA ecosystem. At the core is the SAP HANA database hosting Predictive Analytic Library and Automated Predictive Library. These provide the core classification algorithms. This architecture ensures efficient, scalable, and secure classification while leveraging the performance advantages of in-database processing. Let's discuss key choices that impact the algorithm selection for your classification scenarios. Classification is a fundamental technique in machine learning used to categorize data points into predefined labels based upon their features. It plays a crucial role in various real-world applications, such as predicting whether an employee will churn or remain in the company. The core principles of classification involve supervised learning, where models are trained using labeled data to recognize patterns and make predictions on new unseen data. There are different approaches to classification, each employing distinct methodologies. Some of the most common used algorithms include decision trees, gradient boosting, and neural networks. Each of these are suited to different types of data and classification challenges. Algorithm selection can be guided based upon the data set size to be classified as shown below. For small to medium-sized data sets, logistic regression is used in simple binary classification problems, such as predicting yes or no labels. Nearest neighbors and decision trees are used in cases for easy model interoperability and model explainability. For medium to large data sets, random forests are used for complex classification problems where accuracy is highly relevant. Support vector machines are used for classification scenarios with clear margin of separation, for example, image classification. XGBoost is used in high-performance classification problems, for example, fraud detection. Neural networks are used for complex and high-dimensional data scenarios, for example, speech recognition. Light GBM is used for large-scale in high-performance applications, for example, web search ranking. Multi-nominal native base is used for discrete data, especially for text classification tasks where word counts are used as features for sentiment analysis. For very large data sets, convolutional neural network architecture for images. Recurrent neural networks for sequences of sequence data are used for very large and complex data sets, e.g. natural language processing. Distributed machine learning frameworks such as Spark and Live are used for scalable machine learning scenarios across distributed computing environments. For example, large-scale recommendation systems. AutoML frameworks like SAP HANA Cloud Predictive Analysis Library, AutoML implementation, greatly help users in probing multiple algorithms and parameter variations for a given scenario for selecting the best possible algorithm and model. Let's discuss the key choices that impact the performance of your classification scenario. Model performance metrics are crucial for evaluating and comparing the effectiveness of machine learning models. They provide a quantitative measure of how well a model is performing, helping to identify areas for improvement and guide model selection. Common metrics specific to classification tasks are illustrated below are precision, recall, F1 score, and area under ROC, receiving operational characteristics curve, and AUC, area under the curve. Confusion matrix is a table that summarizes the performance of classification algorithm. It compares the predicted class labels to the actual class labels of a dataset, providing a detailed breakdown of correct and incorrect classifications. This helps in understanding the types of errors a model is making, which can be crucial for improving its performance. Precision, recall, F1 scores are all important metrics for evaluating the performance of the classification model. Precision measures the accuracy of positive predictions, whereas recall, also known as sensitivity, measures the model's ability to find all positive instances. Lastly, F1 score is the harmonic mean of precision and recall. It balances the importance of both metrics, providing a single score that reflects the overall effectiveness of the model. ROCA, UC, or area under the receiving operational characteristic curve, is a performance metric used to evaluate the ability of a binary classification model to distinguish between two classes. It essentially summarizes the model's performance across all possible classification thresholds by measuring the area under the ROC curve. A higher ROCA UC indicates better model performance, and a perfect model having a score of 1, and a random model having a score of 0.5. Data quality is fundamental in machine learning because poor data leads to inaccurate and unreliable models, ultimately hindering decision making in predictions. Machine learning models rely on data to learn patterns and make predictions, so the quality of the data directly impacts the performance of the model. Thus, ensure independent variables are accurate, complete, and free from errors or outliers that could distort the analysis. Data cleaning, outlier removal, and normalization are critical steps in preparing your data. Ensure sufficient data points, especially considering the number of independent variables and the noise level of your data. Validate imputation strategies and model focus techniques like cross-validation. Feature selection is the process of choosing a subset of the most relevant features from a larger set used in a model building. It's a crucial step in machine learning that helps improve model performance, reduce computational cost, and enhance interoperability. In this regard, consider techniques like import analysis or model-based selection to identify the most relevant predictors. The former provides insights into which features are most influential in a model's output, allowing for better understanding of the data model and performance. Several methods exist, including permutation importance, sharply additive explanations, SHAP values, and built-in importance scores from specific models. For instance, SHAP values offer a way to understand feature contributions by consolidating all possible combination of features and calculating their marginal contributions. Let's discuss implementation guidelines for selecting your programming model. For data science workflows, we recommend using Python with the HANA ML library, providing a streamlined, intuitive experience aligned with standard data scientist practice, including convenient data manipulation and integration with machine learning workflows. For alternative approaches, consider SQL script to directly call predictive analytics libraries procedures when tight integration with SAP HANA artifacts is needed. Now let's explore the specific implementation options for each programming model. For Python developers, the HANA ML library is recommended for interacting with SAP HANA Predictive Analysis Library and automated predictive library algorithms. Reference code, includes SAP BTP best practices sample code and SAP community blog post like build your machine learning scenario for your SAP HANA cloud application from Python. For SQL developers, direct invocation of predictive analysis library procedures through SQL script is available when embedding logic within SAP HANA artifacts is a priority. Reference documentation includes comprehensive guides for diverse algorithms. Each approach provides full access to classification capabilities while allowing you to work in your preferred environment. This Python example demonstrates implementing the hybrid gradient boosting tree algorithm for classification using HANA ML. The SAP HANA Predictive Analysis Library hybrid gradient boosting tree algorithm is an SAP HANA optimized gradient boosting tree implementation supporting mixed feature types, continuous and categorical as input. It supports regression in classification scenarios. The hybrid gradient boosting model for classification is trained based upon the training subset, as shown in the figure. The training process requires just a few lines of code. This implementation showcases how quickly you can deploy powerful classification with minimal code through HANA ML. This best practice guide reflects the collective expertise of data science and analytics specialists from across SAP, bringing together insights to support your classification journey. Thank you for watching this session on classification using SAP HANA Machine Learning. We hope the information provided helps you successfully implement effective classification capabilities in your business applications.